One final topic before we are done with capacitors for now is to actually think about the energy stored in capacitors. And to get here, we think about integrating the work done. So we think about a tiny differential amount of potential given to one little charge that is moved a delta V. Now, in order to think through this, you want to think that there's already some charge on our capacitor, which is why it has some delta V, and we're actually putting a new charge there. So what's tricky about this is that by adding this delta Q, we are actually increasing delta V a little bit, right? So as we add more and more delta Q, we are increasing and increasing delta V. So that's why we have to do an integral here. And what we're going to say is that our delta V, because it is actually coming from Q itself, we need to expand that out and note that it's going to be Q over C. So this is however much is already there, right? So that's how much is already there, and then this is the new amount. So when we go to do the integral, 1 over c can come out. Remember that capacitance is a constant which only depends on geometry. So we're not simultaneously shrinking or expanding our capacitor as we do this as well. So that gets to come out, and we are then integrating from 0 to q of q to q. Notice that this is capital Q, this is lowercase. This is the final amount of charge, the total amount of charge moved up. So if we integrate q, you should know that that gives us 1/2 q squared. We have a 1 over c out front, so this is our answer. Q squared over 2c. So that is the total amount of work done, or the total amount of potential energy we've given to charge by charging that capacitor to Q. We can then rewrite it, remembering what I said before, that we can usually measure potential difference, but we can't really measure charge. So what we're going to do is use Q equals C delta V, and we're actually going to plug this in here. We're going to square it. We're going to end up with charge squared on top, but I had a charge on bottom, so that leaves me just with charge, and then I'm left with delta V squared. So that's how we can get that the potential energy stored, and again, you can think of this as work done on charge, in a capacitor is actually 1/2 c delta V squared. And again, we're using that subscript of c to just say that that's the potential difference across the capacitor. So what's a little bit interesting about this is that you're also familiar with this form, right? 1/2 something something squared. Think about 1/2 k delta x squared, for instance, for a spring. So this is kind of like the electrical equivalent of storing energy in a spring, actually. And what's interesting, if you've had differential equations, you might know that mathematically you can create some electrical systems that look just like masses on springs. So that's kind of interesting. So this is the equation we get. Now let's try to interpret that a little bit. But first, what are some applications? There are many different reasons you might actually want to store energy in a capacitor. Now, one is a camera flash. Now, this is a little bit tricky because you might just have a cell phone that has a really bright LED on it that you can also use as a flashlight. But back in the day, there were special things called flash lamps that were lights that were just really quickly discharged and had to be powered by a capacitor. So you would charge up the capacitor, and then the capacitor would let all of its energy go through this little bulb very quickly, making it very bright for a short period of time. So if you think about an old camera, like maybe in an old television show or something where there's that poof and you actually hear a flash, that's due to a capacitor. A second thing that you might be more familiar with is a defibrillator. I'm not going to be able to say it. I'm going to stop trying. So this thingy, for instance, trying to get someone's heart to beat in a regular way. You might also be familiar with this called an AED, where this is just a specific type that does it automatically and talks you through it. So this, again, you need to store a lot of energy and discharge it really quickly, and the way you do that is with a capacitor. You might also find capacitors storing energy in pulsed lasers. And in some uninterruptible power supplies, or what are called UPSs, which you might put on a computer if you're afraid about power going out, if you have a scientific experiment that you need to stay on even if the power goes out. In this case, you can basically store energy in a capacitor as if it is a battery, basically. So these first three are really fast in their discharge, and this last one is very slow in its discharge. But all of them are actually storing energy in a capacitor, so it's something we definitely want to do. What's interesting then is to realize that we're really storing the energy in the electric field itself. So if you were to say, well, where is the energy? It's actually in the field between the plates. So what we can do is we can take our equation for, again, that the energy stored on the capacitors, and now we can take delta V. Again, normally it's a good idea to use that because you can measure it, but we can actually re-express it in terms of E, and we can also re-express, well, E and D, capacitance in terms of its properties, and so we get this new equation. What we're then going to want to do is talk about a quantity called energy density. Notice that we're going from capital U to lowercase u. So this is what we use for energy density, which is just defined to be energy divided by volume. So if you think about the capacitor plate having area A and the distance d, we then have this rectangular prism which we have filled with electric field. Now here we are using a model for a parallel plate capacitor, which means that in fact all of our electric field through here is uniform. So we get to then simplify it this way, and this is our energy density. Notice that our energy density depends on two constants, right? Epsilon naught and 2, those are constants. And then our energy density goes as electric field squared. So not only does the energy density relate to the electric field, it can purely be expressed in terms of the electric field squared. So this is interesting because originally when we introduced electric field, it was just something that simplified thinking about it, right? Something that helped us understand charges interacting with one another without touching. We drew field lines, we drew field vectors, but we said they were just little, representations. We actually now can say that the electric field is a real thing, because where else is this energy? We have energy density in the field. So if we said, well, the field isn't a real thing, well, where is that energy then? So this is one of the things that physicists like because we think that it proves the existence of fields. You're welcome to still be skeptical if you would like. But it is helpful to be able to calculate the energy stored in a capacitor. And again, you can do it using capacitance and potential. So these are the measurable known quantities. You can do it in terms of the electric field and the size, or you could then simplify this form down into energy density, which goes as electric field squared.